Welcome to the third video in our third class session set of videos. In this video, we're going to be embarking on a study of molecular orbital theory. Hopefully we'll get through diatomic hydrogen, diatomic helium as a theoretical study, and maybe we'll even see beryllium hydride. Who knows how far we'll get. Anyways, in MO theory, atomic orbitals combine to give molecular orbitals. Here's an interesting rule and simple to memorize. The number of atomic orbitals that are combined always equal the number of molecular orbitals that are formed. So let's consider diatomic hydrogen, H2 gas. Here we have two hydrogen atoms, each with their one electron. And here they come together to form a bond between the two nuclei that we represent as a line. And we know that line contains the two electrons that we use to form it. And of course, we let off heat in this process. Forming bonds releases heat, breaking bonds, it takes heat. So somehow these electrons are getting into a lower energy state in the process of forming this bond, and they release that energy in the process. Well, what orbitals are involved in making the diatomic hydrogen bond? Well, we know that each hydrogen brings a 1s orbital to the table. That's where its electron is localized in the ground state. So we form two molecular orbitals, and what two molecular orbitals could those be? Well, they could be a molecular orbital which we describe as sigma bonding. So sigma is a Greek letter we use to symbolize molecular orbitals. And this is an in-phase combination. So what does in-phase combination mean? It means that the phase of the wave function that describes the position of this electron is going to be the same sign as the phase of the wave function that describes the position of the electron on the other hydrogen atom. And so if they're both positively signed wave functions, that means when they overlap, they're going to constructively interfere. That is, the wave functions add together. And so you get a greater probability of finding the electrons between the two nuclei at some space between the two nuclei. Another way we could combine the wave functions of these 1s orbitals is we could have one with a positive sign and the other with a negative sign. It's the square of the wave function that just, is proportional to the probability of finding the electron. So it's okay to have a wave function with a negative sign. But if we try to do that, then when those wave functions come together and try to overlap, well, the negative sign on one wave function cancels out the positive sign on the other, and so you generate a node. And this is described as the sigma star antibonding molecular orbital. This is an out-of-phase combination of the wave functions that describe the 1s orbitals. So, two atomic orbitals, two molecular orbitals. Pretty complex stuff. Chemists like to draw diagrams when they describe molecular orbitals, and it helps us see things in terms of relative energy, and that can be useful. So in the next page of notes, we have a diagram, an MO diagram for the diatomic hydrogen. So we're bringing together a hydrogen on the left that contains one electron in a 1s orbital, and the hydrogen on the right that contains one electron in a 1s orbital. And the combination in which those two wave functions overlap, it just so happens to be a molecular orbital that's lower in energy than either 1s orbital on its own. So that's where the sigma bonding goes in terms of energy. Interestingly, as far down in energy that the sigma bonding molecular orbital is pushed, the sigma star antibonding molecular orbital is pushed up the same degree in energy. And so we already described what those molecular orbitals look like. What is interesting about our molecular orbital is it can hold a total of 2 electrons. And so both electrons go into the sigma bonding because we fill the low energy orbitals first, right? Just like water fills the bottom of the glass first, not the top part of the glass. So the sigma bonding molecular orbital is lower in energy than the 1s orbital. The sigma star antibonding molecular orbital is higher in energy by the same amount than the 1s orbital. And I don't know if you recall bond order from general chemistry, but bond order is symbolized as BO. It's the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals, all divided by 2. So what is the bond order for diatomic hydrogen? It is 2 minus 0 divided by 2, or 1. And that's about what we would expect in terms of bond strength between two hydrogen atoms. We'd expect a single bond. Let's see why helium can't form diatomic helium. Well, if we tried the same exercise, we'd be bringing two 1s orbitals together. Each 1s orbital possesses 2 electrons. We'd form 2 molecular orbitals, and we'd have a sigma bonding molecular orbital and a sigma antibonding molecular orbital, and each molecular orbital holds 2 electrons. And so we can see that there's no net energy gain, right? For the 2 electrons that drop in energy, we've got 2 electrons that go up in energy by the same amount. So if there's no net energy advantage, why would helium want to get together as a diatomic molecule? So the bond order for diatomic helium would be 2 minus 2, which is 0, divided by 2, which is still 0. So we would not expect any bonds between the 2 helium atoms. However, what's interesting is sometimes you can knock an electron out of a helium atom. It takes like a little bit of lightning, which sometimes we are able to see in certain instruments that we run noble gas, as a carrier gas through. Sometimes we knock an electron out of helium, and then all of a sudden we see diatomic helium cations. And this is okay, because what we've done is we've only given 3 electrons to the molecular orbital diagram. So we'd have 2 electrons in a bonding molecular orbital and only 1 in the anti-bonding. So the bond order for the diatomic helium cation would be 1/2. So not a very strong bond, but it still sticks together, definitely long enough for us to see it in a mass spectrum. I think I'll go ahead and end this particular video here. I think one of your questions assigned in the book is about diatomic helium. We'll go ahead and try to extend this further using the valence shell electron pair repulsion theory that hopefully you discussed in general chemistry in our next video lecture.